Skylab Houston, everybody around here has looked at the bird and it looks real good.
Roger, roger.
And you're being awaited by the USS Ticonderoga. And we're waiting to see you back here in Houston, too.
All righty. You can relay to the Tyco. We've got their Fox Corpin and our hook is down.
Roger that.
This was Skylab on the final day of the first manned mission.
And if you got
The crew had this last view as they made preparations for return to Earth.
Give it to you here.
It had been a successful mission.
It's,
The large majority of scientific objectives were accomplished.
10 miles.
But the bright orange sunshade, the single solar wing, presented a striking reminder of a mission that was something more than routine. A mission that gave new meaning to the term manned spaceflight.
Minus 13, 12, 11, 10, 9, 8. We have ignition sequence has started. 6, 5, 4, 3.
It was the afternoon of May 14, 1973, when the unmanned Skylab Saturn workshop was hurled aloft at Cape Kennedy, on the way to its assigned orbit 236 nautical miles in space. The cloud cover was heavy on launch day and prevented tracking cameras from seeing an event that occurred about 1 minute into the mission. At the point of maximum vibration, telemetry sensed premature deployment of the meteoroid shield, followed by a weak electrical signal from the workshop solar arrays. Clearly, there had been a problem, but the exact nature wasn't known until after orbital insertion. During the first revolution, Skylab temperatures began to rise rapidly, and pieces of the puzzle started to fall in place. NASA engineers surmised that the anomalies were most likely related. It was felt that the meteoroid shield had been completely lost at deployment, which accounted for the high heat levels. Also, that fragments of the meteoroid shield had jammed or otherwise hindered full deployment of the solar array panels. Failure of these panels, which were designed to furnish about half of Skylab's electrical power, meant that the total power burden would have to be borne by solar panels of the Apollo telescope mount. By early evening, workshop temperatures had risen above the level of safety. Launching of the crew the following day received an indefinite hold, pending satisfactory solutions. Flight support and engineering teams were immediately set in motion to find the answers. At stake was the future of the entire Skylab program. The most urgent need was to achieve a thermal-electrical balance. This meant maneuvering to an optimum flight attitude for solar requirements that were in direct conflict. Too much solar radiation would drive temperatures higher, increasing the chances of component damage and food spoilage. On the other hand, generation of electrical power to drive heat exchangers and food freezers was wholly dependent on exposure to the sun. While flight controllers struggled to achieve this delicate balance, other teams had the major objective of designing a thermal shield that could be deployed on the workshop to make it habitable. NASA centers and private industry responded with a variety of shield concepts. The most promising designs were released for fabrication. Finally, they were subjected to functional testing. By the fifth day of the mission, the choice had been narrowed to a model called the Parasol. It had good functional reliability, and the crew would be able to deploy it from inside the workshop through a scientific airlock. Another shield, the twin-pole sunshade, would also be carried on the mission as a backup. Here in the Skylab underwater simulator at the Marshall Space Flight Center, crews practiced extravehicular installation of the sunshade in conditions approximating 0G. As for the solar wings, simulation methods were mostly inconclusive. Little was known about the extent of wing damage at this point, and the crew could only speculate on how best to make them deploy. At mission control, solar orientation of the spacecraft had begun to yield positive results. Temperatures, still too high for habitation, were stabilized, and electrical power was sufficient for operating vital systems and equipment. Though still precarious, the situation had been checked. There was reason to believe it would remain stable until the astronauts' launch, now scheduled for May 25th, 10 days behind the original schedule. On the day before launch, the Parasol team raced the clock to deliver the flight article on time. They were down to the last 30-minute extension as the Parasol, packed in the flight canister, was loaded for transfer to Cape Kennedy. In spite of the rigid schedule, hopes ran high that the Parasol would do the job. Attention now turned to the astronauts who would attempt to put it in place. In the early morning hours of May 25th, Skylab 2, with both thermal shields stowed aboard, was well along in the countdown. The crew, meanwhile, made ready to embark on their historic mission. This all-Navy crew consisted of Captain Charles P. Conrad, Skylab commander, a veteran of both the Gemini and Apollo programs. Commander Paul Weitz, who would be Skylab pilot for the mission, had been a member of the support crew of Apollo 12. And Commander Joseph Kerwin, scientist pilot, who would be the first American physician in space. The 10-day delay had been a giant cram course for all concerned, especially for the crew. And their job was only partially complete. The execution of all the planning effort was now solely in their hands. Following a smooth launch, Skylab 2 maneuvered to the proper flight path attitude for its initial downrange orbit. By mid-afternoon, the crew had overtaken the workshop.
TV picture beginning to come in now to the control center. Skylab Houston, we're AOS at Guam for the next 10 minutes.
Callie, the Skylab. We got her in daylight at 1.5 miles, 29 feet per second.
Roger, Pete, copy.
They effected rendezvous and performed a fly-around to assess the damage. Most predictions were confirmed.
Hey, Houston, the meteoroid shield area is solid gold.
Roger, copy.
His brief description is his suspected solar wing 1 and 2, right? No, 2 is gone. Completely off the bird. Solar wing 1 is in fact partially deployed, and the reason that you've got different readings, not symmetric between your 3 solar panels, is there's a bulge of meteorite shield underneath it in the middle, and it looks to be holding it down.
Roger, copy.
Okay, Houston, it looks like the meteorite shield at the upper vent panel on the sand wing has wrapped around it just slightly.
Where are we?
Now, my guess is that our easiest thing to do is just go to the end and try and deploy it.
Roger, Pete, from which side of the SAS is the meteoroid shield slightly wrapped around? Is it on the side of the main tunnel? Or
Before docking, the crew attempted to free the wing.
The other side, Dick.
Although the try was unsuccessful, the TV pictures seen here proved invaluable in devising the technique that ultimately worked. Following a night's sleep in the command module, the crew spent the morning of Saturday, the 26th, activating and checking systems in the multiple docking adapter and airlock module. Later, they were given a go to enter the workshop.
So we are progressing slow but sure, and everything so far is working.
By late afternoon, the canister was positioned in the scientific airlock, ready for parasol extension.
Okay, Pete, we had a little drop out there, some noise. Could you tell us what step you're on?
We're about to put rod delta on.
Roger, copy.
Okay, we had no trouble venting it down. It vented in about 4 minutes, and it held 0 for 10 minutes without any outgassing. Door opened very smoothly, and so far the rod extension has gone very easily, and as I say, we're just taking a little heat break.
Some 4 hours after the operation began, the thermal parasol was deployed. It was then placed in position close to the workshop skin.
Well, we don't think so, Houston. We can see the ends of all the rods. It's completely free of anything. There's nothing hanging it up.
It took about 2 revolutions of Skylab before temperatures began to fall. Projections showed that if the present trend continued, the workshop would be below 100 degrees the following day. It wouldn't be the most comfortable environment, but after a discussion with the crew, the decision was made to proceed the next morning with the normal flight plan. The crew put in a long, trying day activating the workshop. Getting things organized and in the proper place was a chore in itself. However, they were discovering to their satisfaction that moving big pieces of gear presented no problem in the weightless environment. By noon, Monday the 28th, with the workshop completely activated, primary emphasis was on getting the biomedical experiment started. This was the first in a series of lower body negative pressure and vector cardiogram experiments. Paul White's the subject, Joe Kerwin the observer. There followed a workout on the bicycle ergometer to check metabolic effectiveness and to evaluate the bicycle as an exerciser for long-duration missions.
Ideally, the handlebars would be longer than they are now and would kind of sweep down around you so you could grab them in the right place.
Other medical experiments conducted over the next few days included blood samplings from each crew member to satisfy the 5 blood study experiments. Body mass measurement to determine each crewman's daily weight and to validate the use of this device for weighing in 0G. A rotating litter chair, a part of the human vestibular function experiment, tested for motion sickness, rotation perception, and ability to determine orientation. In addition to these and other medical experiments, science experiments were simultaneously being performed. Here, Pete Conrad operates the Apollo telescope mount control and display panel in preparation for the solar physics studies. In subsequent operations, data such as this active region of the sun was recorded by the telescope.
Weird sound, but it's pretty collaborative.
Right. Got a tape motion light.
The Earth resources experiments also got underway after activation of the 6 remote sensing systems.
Mark, S-192, I got a ready light.
We just came out from over the clouds. How about that?
Auto sequence start on 90 and you EPC go.
From a broad field of view provided by this large space platform, the systems began photographing selected portions of the Earth's surface in the visible and near-infrared spectral regions.
There went out.
Although the crew had earlier encountered a number of equipment problems, the result of excessive temperatures, the prospects now looked bright for a full 28-day mission. The temperature had stabilized in the mid-70s. The food was good, and so was morale. And up to now, the 4,700 watts of available power appeared to be adequate as long as high-load experiments were staggered. However, by the 5th day, some of the storage batteries had begun to perform in a degraded manner. The power shortage grew critical, and it became apparent that to carry out the mission, the jammed solar panel would have to be deployed. Meanwhile, at Marshall, in the underwater simulator, techniques were being developed based on TV coverage of the solar wing. Using only tools and equipment like those aboard Skylab, the backup crew developed a set of procedures they felt would do the job. On June 7th, astronauts Conrad and Kerwin made their exit to put the plan into operation.
Just take your time. Okay, Houston, we're out there. We have the debris in sight. There looks like enough room to get the cutter, and I'm trying to help Joe stabilize.
As the simulations had shown, access to the solar wing was the big problem, what with few handholds or foot restraints. It was solved by joining pole sections of the twin-pole sunshade, anchoring it by hooking a pair of cutters onto the strap that held the wing. Thus, a temporary handrail was fashioned that allowed Pete Conrad access to the solar wing, where he attached the tether. The cutters then severed the strap, and the tether was pulled taut to free the wing actuator. After the crew returned to Skylab, an attitude change placed the solar array system into the sun, where, after a period of warming the hydraulic dampers, the panel arrays fully deployed. Within hours, the electrical power surged to almost double the previous level. It meant that the power management scheme could be abandoned, and the original flight plan could be resumed. In the days that followed, the nagging problems that had plagued the astronauts from the start began to resolve. The mission began to sound much more routine, more like a normal working day. Experiments were coming off like clockwork, and a wealth of scientific data was being gathered. Experiments such as this one in materials processing. With more leisure, it was not uncommon for the men of Skylab to indulge themselves in the fluidity of movement in zero G. The weightless condition also simplified sleep accommodations. Since there was really no up or down, the only requirement was a sleeping bag type of restraint. And as mentioned earlier, heavy objects were easily handled. It was the small pieces that sometimes got away. But even when objects were lost, they generally turned up sooner or later on the air conditioning screen, there to be reclaimed. On day 29, after performing final closeout of the orbital workshop, the crew donned spacesuits for the return leg of their mission.
Skylab Houston, we're in at-hold CMG. You're go for undocking.
Okay, stand by.
Roger.
Okay, we're free. We got 0.4 of a foot per second, Houston.
Roger.
Bye-bye, Skylab.
After undocking, they remained on station briefly to obtain photographic coverage. Following deorbit, the command module, its heat shield trailing a fiery plume, re-entered the atmosphere. For the first time in about a month, the crew experienced the forces of gravity.
Ticonderoga standing by for sonic boom now.
Skylab Houston through Ra 1. How do you read?
Actually, we leave you back clear, Houston. Everything's okay. We're out of 40,000.
Very good, Pete. You're in the groove.
Hello, recovery, Skylab. On the main, everything's okay. And this is recovery. We have a visual below the overcast, about 100 at 050, 6 miles from Ticonderoga. Recovery splashed down, and it looks like stable one. Ticonderoga, roger, out. Hello, recovery, Skylab, do you read? Recovery, read you loud and clear. How's it going? Okay, everybody's in super shape. That's great. Welcome back. Thank you.
Splashdown occurred some 700 miles off Southern California, near the recovery ship, the USS Ticonderoga. After retrieval and positioning on the flight deck, the command module hatch was opened. One by one, the crewmen stepped forth unassisted, seemingly undaunted by their return to normal gravity. They accommodated to normal activity within several hours. In San Diego, the first Skylab crewmen were received by a vocal and appreciative throng. They had reason to be proud. The large majority of scheduled experimental data was gathered, and all subsystem operational test objectives were achieved. All this in spite of the problems encountered from the start. Problems that in the final analysis required the presence of man to reason, to decide, to execute solutions as only he can.
Earth view. Sounds far-fetched at the moment, doesn't it? But you know, we may be seeing ads like this in the not-too-distant future. In fact, there's the equivalent of a small bungalow out there in space right now that's empty and available, with a beautiful view of Earth. Skylab, a bungalow that has already had 9 tenants. The main purpose of Skylab was to make space flight more useful for man's endeavors on Earth. As NASA Administrator James C. Fletcher put it, Skylab marked the transition from exploration to the exploitation of space. As has been said, the average taxpayer is entitled to ask, what's in space for me? Well, the results from Skylab will, we hope, answer that. Let's take a look now at the development of the Skylab space station itself. As I said before, this was really an economical venture to which the earlier major space programs contributed greatly, enabling the Skylab project to use flight hardware already in existence. It's 48 feet tall and 22 feet across, with a 13,000 cubic foot interior, 10,000 cubic feet of working space in the main section alone, the equivalent of a small family bungalow. Skylab is divided into a lower floor with crew quarters, wardroom, and medical experiment area, with an upper floor for space technology equipment. The multiple docking adapter provides docking ports for the command module, as well as housing the control console for the solar telescopes, and a series of cameras for conducting Earth resources observations. The command module used to take the astronauts to and from Skylab is identical with that used on the Apollo flights and left over when that program was cut back. So, as we can see, much of the hardware needed for the Skylab program was already available. The unmanned orbital workshop was launched in May of 1973 atop a Saturn V rocket from Pad A, right here at Kennedy Space Center in Florida.
10, 9, we have ignition sequence start. The engine's now building up to 7.7 million pounds of thrust. We have a launch commit and we have a liftoff. The swing arms moving back.
When the flight was scarcely a minute old, a serious problem developed with the workshop. Mounting temperatures in the workshop indicated the failure of the meteoroid shield, which was actually torn off by the slipstream during launch. An hour after launch, the ground controllers in Houston were still waiting for confirmation that the workshop's solar array panels had deployed, a signal they never received. Of course, the launch of the first Skylab crew scheduled for the next day had to be postponed until solutions were found. The urgent need was to stop the rapid temperature rise, which was immediately accomplished by ground control in reorienting the workshop so it was no longer broadside to the sun. The next 10 days were hectic. Immediately, teams were formed to provide answers to the problems. A major objective was to design and fabricate a thermal shield that could be deployed on the workshop to make Skylab habitable. Throughout the United States, teams worked round the clock in an all-out effort to perfect such a design. Meanwhile, here at Marshall Space Center in Huntsville, Alabama, crews were evaluating installation of a parasol device in the Skylab underwater simulator. In conditions approximating zero-G, they also trained underwater in methods of freeing the jammed solar panel. But the actual work would have to wait on an eyewitness assessment by the astronauts in space. Time was becoming critical if Skylab was to be saved. Relief would come only from the thermal shield parasol, which would be deployed by the astronauts when they arrived at Skylab. During the early morning hours of May 25th, almost 10 days after the original schedule, a Saturn 1B was ready to launch an Apollo spacecraft for the first manned visit to the Skylab orbital workshop, with astronauts Conrad, Kerwin, and Weitz aboard.
We have launch commit and
Skylab 1 was on its way, the first step in the fulfillment of an opportunity to use men in space for practical humanistic benefits. By mid-afternoon, the crew rendezvoused with Skylab and performed a televised fly-around to assess the damage. Most of the predictions were confirmed. The meteoroid shield had been ripped away, exposing the workshop's skin to the sun. One of the solar array panels had been completely torn off, and the other, only partially deployed, was held in check by an aluminum strap, a fragment of the meteoroid shield. As astronaut Conrad put it,
Expected solar wing 1 and 2, right? Is gone.
an unsuccessful attempt was made by Weitz at freeing the panel, working in the open hatch of the command module before docking with the workshop. After a night's sleep aboard the command module, they entered the workshop and took steps to deploy the parasol. In mission control, optimism that the mission would be saved wasn't long in coming, as external skin temperatures began dropping rapidly, and within the workshop, too, they had started to fall. The parasol was doing its job, but there was still a shortage of electrical power. The stuck solar wing would have to be pulled out fully. Thanks to the work of the backup crew at Marshall, where procedures were worked out for freeing the solar panel.
All the attention I can take.
Astronauts Conrad and Kerwin went on their first spacewalk to repair the damage. This took 3.5 hours, and it was difficult work. But man prevailed, and they were able to sever the strap and pull out the panel.
there she goes. Let go, let go.
All right.
It's got it.
Within hours, the power situation was nearly normal. The mission could continue. A mission transformed from near ruin to success. From the beginning of manned space flights, there's been a concern about the ability of man to survive flight through space and be able to perform satisfactorily in prolonged periods of weightlessness. This was a major concern and objective of all three Skylab missions, and was especially true on this mission. For the first time in space, there was a medical doctor aboard who supervised the tests in the Life Sciences program, astronaut Dr. Joseph Kerwin. This lower body negative pressure test provided valuable information on the cardiovascular system, carefully checked and monitored on the control panel, which supported all medical experiments. A measure of motor sensory performance, an experiment designed by a high school student, using a punchboard apparatus for eye-hand coordination to measure changes in motor sensory skill of the crews. Balance, orientation, and perception, so important to man's ability to function efficiently in space, was another of the life science tests. The astronauts were instructed to exercise frequently, and one of the techniques was the ergometer, or bike, to help keep them in shape. This also served as a test for possible changes in metabolic activity while working and living in a zero-G environment, as well as a check on heart rate and blood pressure under these workloads. Throughout each mission, a vast number of tests were made on eyes, ears, nose, throat, and blood samples were taken and returned for post-flight testing. Actually, we've seen only a small portion of the medical tests covering muscle and bone development, heart and blood tests, perception and equilibrium, and even cell growth. The ability to monitor, record, and transmit medical information over such a distance on the most advanced equipment yet devised will prove invaluable and undoubtedly be adapted for use in hospitals here on Earth. The tenets of Skylab certainly indicated that men could live comfortably in space for long periods of time with no apparent harm. It can be said that with Skylab, we have completed the most extensive medical space missions ever flown and learned many new things about man in weightlessness. Outer space is a truly revolutionary platform for materials processing, since all of the adverse effects of gravity are absent. This makes it possible to perform operations in materials processing and manufacturing that would be virtually impossible here on Earth. Many space processing experiments were performed aboard Skylab in a vacuum chamber and heat treating apparatus, including an electron beam gun and small electric furnace. The formation of crystals might well be the most valuable of all the manufacturing experiments. This resulted in crystals 10 times larger than those grown on Earth, with a much better uniformity of composition, so important in the modern field of electronics. This will result in systems that will perform more functions, will be faster, will require less power, will be smaller and less expensive to manufacture. The pocket computer, so widely used and popular today, is a direct result of space technology. As Professor Harry Gatos of MIT says, it is no longer a matter of speculation that materials processing in space presents one of the greatest opportunities ever afforded to benefit mankind. And kids, when it comes to blowing bubbles, how about this? Puncture them. Pull them and pick them up, but they still won't break. As you can easily see, getting from place to place is no problem in Skylab. Weightlessness can be lots of fun, too, as Pete Conrad shows as he exercises, much like a squirrel in a cage. circus acrobat or Olympic swimmer can match this. We all know Alan Shepard was the first to play golf on the moon. Well, here's the first space ball game ever played. The first 3 tenants of Skylab returned to Earth after 28 days in space. When trouble developed at the start of this mission, we might have despaired and written off Skylab as so much space junk. However, that was unthinkable. What the ground teams and astronauts did in saving the project, moreover, proved the crucial value of man in space. Future missions were assured. Early one morning, late in July, a month after the return of the first crew, Skylab 2, the second manned mission, was launched, with astronauts Bean, Lausma, and Garriott aboard.
And the second manned crew has cleared the tower.
During the 8-hour chase of Skylab, one of the 4 thrusters used for maneuvering their command module sprung a leak. Mission Control ordered the astronauts to shut the leaking assembly down. Bean still managed to dock perfectly. Six days later, another thruster sprang a leak and had to be shut down. The thrusters are needed to orient the capsule so that its main rocket can fire in the right direction for safe re-entry and return to Earth. For the first time in the manned space program, NASA had developed the ability to perform a rescue in space from a disabled vehicle. Round-the-clock preparations were immediately begun to activate the Skylab rescue vehicle, the rocket assembled and an Apollo craft modified. The Saturn 1B rocket was rolled out to the pad, ready to launch the rescue ship into orbit. Meanwhile, the 2 leaks were found to be unrelated and not as feared indicative of a general system breakdown. Computer studies and ground simulations showed that the capsule could be steered with half its operating thrusters, and the astronauts were told they could stay aloft for the 59 days as planned and continue their scientific studies and experiments. The most important package of scientific instruments on Skylab was the 12-ton telescope mount with its 8 solar telescopes to permit a study of the sun. The importance of these studies and benefits cannot be exaggerated, especially when we consider the natural resources and energy crunch that is upon us today. The possibility of this research teaching us how to better harness this energy to power our cities and homes with an inexhaustible supply of clean, non-polluting power becomes a major goal. When people think of astronauts, they usually visualize them as high-ranking military officers and daring test pilots, forgetting that some are also scientists with advanced degrees in physics, electrical and aeronautical engineering, and medicine. The value of men in space as true scientific partners in space science research is most evident in the Solar Studies program, because that allowed photographic film to be used, resulting in spectacular photographs being returned to Earth. Pictures such as this can only be made from space above the Earth's atmosphere with a special instrument, a spectroheliograph. Notice the comparison of the size of Earth with the large eruption of the sun's atmosphere. Other wavelengths were used to help follow changes in the sun apparent when this photograph was analyzed. Such X-ray photos permitted further coronal study, unveiling faces of the sun never before seen by Earth-bound observers, giving radically new knowledge of the sun and ways it may affect the Earth. Solar studies and stellar astronomy were features of all 3 Skylab missions, and this solar flare, photographed on the 3rd mission, was the most spectacular ever recorded, radiating more energy than has been used by man since the beginning of civilization. The sun has no energy crisis. It puts out the entire annual world energy demand thousands of times each second. This gives added meaning to the words of Wernher von Braun when he said, "We hope one of these days to harness this energy on Earth." High priority was also placed on a machine that would allow an astronaut to move freely about outside a spacecraft. Using the Skylab's upper dome area to explore this kind of flying characteristic, the astronaut uses a maneuvering unit which could shuttle him between spaceship and satellite. This will prove to be invaluable in space flights of the future. There were also 19 experiments carried out specifically for high school students. One brought other passengers aboard Skylab 2, the Spiders, Anita and Arabella. This was an experiment to find out the structure of the web they would spin in the weightless state. They soon adapted to space and spun a web quite easily. There was a problem, though. When they ran out of food for the Spiders, they shared bits of filet mignon with them. Oh, for the life of a spider in space. The Skylab 2 crew spent almost 14 hours in spacewalks, augmenting the parasol with a twin-pole sunshade, changing film for the solar telescope, and retrieving canisters containing over 77,000 pictures of the sun from outside the workshop. After 2 months and some 24 million miles, the scientific journey of Skylab 2 ended, bringing back scientific data and secrets of the sun that had been kept secret for billions of years by the dense blanketing of Earth's atmosphere. In November, after a 6-day delay to replace cracked stabilizing fins, the third mission soared along, with astronauts Carr, Gibson, and Pogue.
Lift off, the engine's building up to 1.6 million.
Skylab 3, the longest of the manned space missions. One of the major projects on all 3 Skylab missions was the Earth Resources Experimental Program, which will certainly show the man in the street that space can be of everyday use in solving some of the world's most pressing problems, such as pollution, locating resources, and feeding the hungry. Special cameras were designed for this work. This program again brings out the importance of having men in space, for the astronauts were trained to observe specific places on Earth. They brought back photographs such as these, taken in the visible and near-infrared wavelengths, resulting in countless discoveries about the Earth in many different fields, in the inventory of water resources and study of pollution, seen so clearly in this photo of Lake Michigan in the Chicago area, in regional planning and development. Here we see the densely populated area of Baltimore and Washington, D.C. Information obtained will result in better warnings given of impending storms, such as the astronauts observed from space in the Caribbean and Pacific. This photograph of Hurricane Ellen in the North Atlantic revealed that the walls of the eye of a hurricane were sloping, which caused energy to be fed into it, a fact heretofore unknown and of utmost interest to meteorologists. In agriculture, for crop census and yield, soil moisture, and crop infestation. For example, in photographs of the desert areas of Africa, discoveries were made of the extent of damage caused by drought and incorrect cultivation methods. Valuable discoveries were also made in the field of geology to help locate natural resources, minerals and oil, so important to the world today in the light of critical shortages. Faults and changes in plate motions of the Earth, never before seen by man, were observed and studied, as were forests and range. Oceanography, the study of current flows and eddies, such as the Falkland Current, never before photographed. Aids to ship navigation, to lessen the possibility of damage to cargo and ships, and reduce the chance of major oil spills. Mapping, especially in such areas as this in South America, never before done accurately. This perspective from an orbiting spacecraft, such as Skylab, gives us a better way to inventory and monitor our resources, and provides us with information at a cost we can afford. While it will take years to study and analyze the thousands of pictures taken from Skylab, we cannot overestimate their actual value in improving our life here on Earth. Meanwhile, let's go back to the comfortable environment of life in space. And speaking of comforts, the comforts of home were not neglected either, as the astronauts could enjoy weekly showers. And if they could find a foothold, wash and shave, and even prepare their own food to individual taste. No more just eating out of a tube, as on earlier space flights. Crewmen enjoyed space luxuries never before available. Even man's sleep was monitored by a cap with sensors, as each astronaut bedded down vertically in a sort of sleeping bag in his individual sleep compartment. Or should I say, stateroom. It was found, by the way, that the quality of sleep compared favorably to the astronaut's normal sleep pattern on Earth. Determining weight in a weightless world is a real problem. With no gravity, there is no weight, and normal scales cannot be used. Since many of the biomedical experiments require measurement, this odd-looking chair was devised and used to keep a careful check on the weight of the astronauts. Small masses were also measured on a device so sensitive it could determine the weight of a postage stamp. The next time you do your push-ups, try this. It was quite a chore when the astronauts got ready to go outside for a spacewalk. Fast-action photography, however, makes it look easy. It is much like suiting up Junior to go play in the snow. The Skylab crew spent 21.5 hours outside the workshop in spacewalks, changing and retrieving film, observation, and repairing equipment. As on all three missions, Earth observations continued. While Skylab centered most of its work on practical uses of space, its crew didn't neglect precious opportunities to enrich science's knowledge. Cameras zeroed in on promising targets of opportunity, of which the most noteworthy was the comet Kohoutek. While its observations from Earth were not as spectacular as hoped for, Skylab's solar telescopes plus 2 spacewalks with portable cameras gained amazing results. Actually, the Skylab instruments were the only means available to scientists anywhere to observe the comet during its close passage to the sun, as this stop-motion film shows. The fact that the astronauts were able to observe the comet at this time and even make sketches proved scientifically valuable in collecting basic data needed to make the greatest advance in cometary research since Halley's time. While we were celebrating the holiday season of 1973, each in his own way, there was a special celebration aboard Skylab 3. The Skylab Christmas in Space. And of course, that included the stockings, hung by a very unusual Christmas tree, painstakingly constructed out of food cans and decorated by the astronauts with a very special star on top, Comet Kohoutek. And now, a Christmas message from space, showing concern for people everywhere.
From the Skylab 3 crew, we wish to extend to people around the world the message of peace, goodwill, and human understanding.
After setting a new record of 84 days in space, the third manned Skylab mission ended with a splashdown and recovery in early February of 1974. It's impossible to single out one thing as the most important among the more than 2,400 experiments performed during the Skylab missions on a flight path that covered almost 75% of the Earth's surface. It is certain, however, that Skylab has established a basis of factual data for the design of future space systems and the planning of future manned operations in space. Even more important, it has demonstrated that man has important work to do in space. And for humanity in general, there is no doubt that this use of space makes an important contribution in allowing man to manage his affairs here on Earth more in harmony with nature. Before the crew left the space bungalow, they configured it for a possible revisit by somebody, perhaps by the future space shuttle, or as the space administrator said, the little green men from space. The orbital workshop will continue in a 270-mile-high orbit for 10 years or more. It's up there right now. Maybe you'd like to be the next tenant. 4 rooms. Beautiful Earth view.